So I'm VaughanJones. A knot can actually be used as a source of some kind of physical model. So for instance, if we have a knot, such as this one here, then one is to think of this picture of a knot as defining some kind of system with atoms at each of these crossings. So this particular knot has 6 atoms, and these atoms are interacting with each other according to the scheme given by the knot itself. So this atom interacts with this one, and with this one, and so on. This one interacts with its 4 nearest neighbors on this particular picture. Let's say that every atom can be in a total of 2 states. That's in the very simplest case. The model is defined by giving some kind of energy to each interaction. So if this atom is in the plus state and this atom is in the minus state, the model will specify how much energy is associated with that particular configuration. Given a global configuration of these states, so you know for each one of these atoms whether it's plus or minus, the system responds with a total energy, E. And the basic Gibbs postulate in equilibrium statistical mechanics is that if you have a system like this at equilibrium, then the probability of observing a given state is proportional to the exponential of minus some constant times the energy of that state. The partition function, traditionally written Z, is simply the normalization constant for this probability. So as I said, the probabilities are proportional to these. Probabilities have to add up to 1, so we define the partition function to be the sum of all states of exponential of minus ke to the state. From a mathematical point of view, it would seem like there's not too much interest in this for the study of knots, because knots live in 3 space. On the other hand, everything that I've said here has to do with the 2-dimensional picture of the knot. The whole physical system was set up with crossings, for instance, and the crossings don't exist as 3-dimensional entities. So up until, say, 10 years ago, one would never have thought of trying to use this approach to study knots. However, it has turned out, maybe surprisingly, to be extremely useful. The key idea is the following. Is it possible to choose the parameters of the model, the number of spins here per side, the size of the interactions, the temperatures and so on, in such a way that this partition function depends only on the knot as an element of 3 space and is independent of the actual picture that you draw? This program has had positive results, surprising though it may seem a priori, and indeed it is possible to get lots and lots and lots of different invariants of knots using this procedure according to how you define the parameters of the system. But there's no reason to stop there. One could be interested in the correlation functions of the system, which would give the correlation between the atoms on different sites along the knot. A priori, once again, there's no reason why this should have any 3-dimensional meaning, but since the partition function did, maybe one should hunt for meanings to that. From a physical point of view, one has a source of lots and lots of different systems by varying the pictures of the knot, varying the topological type of the knot. Another thing that the physics are just looking at is larger and larger knots, so one could try to look at extremely large regular patterns, for instance, and try to study the polynomial invariant of these patterns asymptotically as the pattern becomes larger and larger. This is something that seems to be hardly touched on at all in knot theory, but it's very interesting from a physics point of view. For instance, there's a famous unsolved problem in physics called the Potts model. And one can actually show that if you knew enough about one of these polynomials, in fact the one that I first discovered, if you know enough about that polynomial, you can actually solve the Potts model. In other words, the Potts model is somehow equivalent to knowing the asymptotics of Vk of t for a certain class of knots, a certain very regular class of weaves known as French sonnets or tresses anglaises, depending on whether you were English or a French sailor. The kind of weaves that you would have with a hammock, some regular weaving pattern which is repeated all over the hammock. So if you knew enough about polynomials for hammocks, you could actually solve the Potts model. I find that rather interesting.